Thanks for tuning in to First Principles Daily, episode 24, for June 29th, 2026. Monday, a fresh First Principles teardown to start the week. Indoor farms sell lettuce at premium prices, yet the electricity to replace sunlight often exceeds the value of the crop itself. Vertical farms stack crops in controlled rooms and promise reliable, local harvests without weather or long supply chains. The finished head of lettuce reaches the store at prices several times higher than field-grown equivalents, even though the seeds and water involved remain inexpensive commodities. The gap appears because every photon that drives photosynthesis must now be generated, paid for, and removed as heat. This turns what the sun supplies at no marginal cost into a continuous purchased input. The same sealed environment that protects against pests also traps the waste heat from every watt of lighting. Operators must therefore size and run chillers and dehumidifiers that would otherwise sit idle in an open field. The hidden energy tax inside premium lettuce shows up in the numbers right away. A rough magic wand estimate begins with the raw inputs that actually end up in the harvested plant. A typical head of lettuce contains on the order of a few grams of dry matter, mostly carbohydrates and water, whose commodity value as bulk biomass is measured in cents. Adding the cost of seeds, nutrient salts, and the small amount of water transpired gives a material floor well below $1 per head. It probably sits closer to a few tens of cents. The finished retail price, however, sits several dollars higher once the farm's energy and capital charges are included. Dividing those two figures produces an idiot index on the order of 10 to 20 or more. This depends on the exact electricity tariff and utilization rate of the facility. The gap does not reside in the seeds or the water. It resides in the continuous conversion of electricity into photons and then into heat that must be pumped back out. Lighting alone can consume 10 to 20 kilowatt hours per kilogram of fresh produce in many reported installations. The subsequent cooling load adds another comparable increment. Each kilowatt hour carries a monetary cost set by the local grid. Every hour of operation adds to the depreciation of the lighting and HVAC equipment. Because the building shell itself was never designed as a photosynthetic reactor, additional capital is spent on insulation, vapor barriers, and structural reinforcement for the stacked trays. These layers compound. Higher electricity use drives larger HVAC equipment, which raises both capital and operating cost. That in turn requires higher throughput or higher prices to recover the investment. The idiot index therefore signals that the dominant expense is the engineered system required to stand in for sunlight. It is not any scarcity in the atoms that form the lettuce. One might object that falling LED prices or rising field labor costs could close the gap. Yet the second law conversion losses remain fixed. Every photon generated electrically still deposits its full energy as heat inside the envelope. So the cooling load scales directly with photon delivery regardless of how cheaply the LEDs themselves are manufactured. Even if fixture prices halved, the electricity required to run them and the larger chillers needed to reject their waste heat would continue to dominate amortization schedules. The same arithmetic applies to water. Although indoor systems recirculate most of the transpired moisture, the energy cost of moving and chilling that water still traces back to the photon input. Warehouse templates that never question sunlight keep this burden locked in place. Conventional indoor vertical farms follow a pattern of incremental improvement on existing building and lighting systems rather than redesign from the physics of plant growth. Operators lease or construct warehouse space, install multi-tier racks, and illuminate each layer with LED arrays sized to deliver photosynthetically active radiation at intensities comparable to sunlight. Because the rooms are sealed, every watt of light eventually becomes heat that must be removed by chillers and dehumidifiers. This adds another large electricity load. Capital is tied up in the racks, the lighting fixtures, the HVAC plant, and the automation that moves trays, all of which must be financed and amortized over the life of the facility. Labor and packaging remain, but they are secondary once the facility is running. The result is that energy and capital recovery together account for the majority of operating cost. a structure that feels normal inside the industry because every new project starts from the same template of leased space and purchased fixtures. Field agriculture, by contrast, receives its photons at zero direct cost and sheds heat to the open air. So its cost structure never encounters this double burden. The current price of indoor produce therefore reflects the accumulated decisions to treat lighting and climate control as purchased services rather than as variables to be minimized at the level of fundamental energy balance. Even when operators adopt more efficient LEDs or variable speed fans, the underlying requirement to generate and then reject the same quantity of photons persists. Incremental component swaps rarely alter the dominant cost centers. Building codes written for human occupancy rather than photosynthetic reactors further dictate ceiling heights, fire suppression, and structural loads that add unnecessary mass and volume to the envelope. Financing models treat the entire installation as a single depreciating asset. This spreads the cost of over-designed HVAC across every kilogram of output, whether or not the crop actually needs that level of climate precision. These interlocking choices compound because each new facility is permitted, financed, and equipped as a one-off rather than as a repeatable photosynthetic reactor whose energy balance has been optimized from first principles. Moving the boundary, not erasing it, requires attacking the energy balance directly. One path is to locate facilities where electricity is already near its marginal cost floor, such as regions with persistent surplus renewable generation or co-located with industrial processes that produce low-grade heat. A second move would be to redesign the lighting and growing plane together. This way, a larger fraction of emitted photons actually reaches leaf surfaces and a smaller fraction is absorbed by walls or converted to heat that must be removed. This might involve custom optics, dynamic intensity schedules matched to plant development stage, or even moving away from full indoor containment towards structures that emit diffuse natural light while still controlling temperature and pests. A third step would be to standardize the entire mechanical package. Racks, air handling, and tray movement could then be manufactured at scale rather than assembled on site for each project, thereby cutting the capital component that currently dominates amortization. Each of these changes requires a different enabling condition. Cheap power needs transmission or siting policy. Better photon delivery needs optical and horticultural engineering. Standardized equipment needs volume production and repeatable building codes. The hard limits are real. No amount of redesign removes the second law losses when electricity is turned into light and then back into heat. So calories and staple grains will remain uneconomic indoors at present electricity prices. The opportunity is bounded to high-value, short shelf life, pesticide-sensitive crops where the premium for locality, consistency, or water savings can cover the remaining energy cost. The first concrete signal that someone is pursuing this path would be a facility whose power purchase agreement or on-site generation visibly decouples lighting cost from retail electricity tariffs. This would be combined with published energy use figures per kilogram that fall well below the current reported range. Even under those conditions, the redesign must still solve the problem of capital intensity. Standardized modules reduce per unit cost only if enough identical units are ordered to justify dedicated production lines, which in turn requires predictable permitting across multiple jurisdictions rather than case-by-case approvals that stretch timelines and financing. When sunlight is replaced by purchased electricity, the price of produce reveals exactly how much of the system is still performing work that free photons once handled at no cost. The second principle is that an idiot index, driven by energy conversion rather than by material transformation, points to a physical boundary, not merely a manufacturing problem. So the viable niche is defined by what the indoor approach uniquely supplies, rather than by blanket replacement of field agriculture. Who will first publish both the siting decision and the measured kilowatt hour per kilogram data that together show the boundary has been moved? That's a wrap on today's first principles breakdown. The ideas travel further when you pass them on. Send this to a fellow builder. I'm Patrick in Vancouver. See you tomorrow. And if you'd rather watch than listen, find us on YouTube at Nerra Network. Links in the show notes. This episode used AI voice synthesis of my voice. Editorial selection and analysis are my own. I'm about to prove